This module introduces what statisticians call the normal distribution. I'll begin by asking you a question. We just reviewed computations for a standard deviation. And if you think about it, we did some rather odd things. We squared things. Then we took a square root at the end. Why did we compute the standard deviation the way that we did? And the answer is the very pragmatic reason that it works. There is a very close relationship between the standard deviation and the data in what's called the normal distribution. What's a normal distribution? Excellent question. I'm glad you asked that. The normal distribution is the distribution that is normal. In other words, what we're saying is this is the traditional bell curve pattern, that whatever quantity it is that we are graphing here, we are saying the most common observations are ones that occur around the middle, that these data values happen most often. Things that are a little bit above average and a little bit below average will happen with slightly less frequency. Extremely large data values will be relatively rare. Extremely small data values will be relatively rare, but we'll see a symmetric relationship throughout. Being a bit above average or a bit below average happen about as often. Being way above average, being way below average happen about equally rarely. The normal distribution is the distribution that is normal. Heights, weights, most physical measurements will follow a normal distribution. Also, scores on standardized tests tend to follow a normal distribution. In fact, the tests are designed that way, which, by the way, is one of the reasons that taking these standardized tests is often a daunting experience, because it's the first time in our academic careers we've taken a test where scores are designed to bunch up around the middle. Normally on an exam, it's designed to have scores bunch up at the top end. But a standardized test, a normal curve, things bunch up toward the middle. And so, for example, heights of adult American males are normally distributed with mean of 5'9", standard deviation of 4 inches. Women are somewhat shorter on average height of 5'5". Also, their heights are somewhat less varied, standard deviation of only 3.5 inches. I got these this information from the internet. I'm going to assume it's true because, of course, everything on the internet is true, right? Let's at least go with these numbers. They seem plausible, at least. What we're saying here is, let's draw a picture. Men, most common height is that average value of 5'9". 5'10" and 5'8", yeah, that's pretty close to normal. That happens about as often. Exceedingly tall individuals, say 6'4", 6'5", and higher, those are relatively rare, as are more, shall we say, vertically challenged individuals. A similar phenomenon obtains for the women, average height of around 5'5". Because the women's standard deviation was smaller, the data will bunch up more. But again, relatively few taller individuals, relatively fewer vertically challenged individuals as well. For a normal distribution, approximately 2/3 of the data will lie within one standard deviation of the mean. Again, this is why we compute a standard deviation the way we do, because of this close relationship with the normal distribution. Start in the middle, go out a standard deviation, you've got about 2/3 the data. Go out 2 standard deviations, you've got about 95% of the data. And wait, there's more. Go out 3 standard deviations and you've got virtually everything. These 3 benchmarks are things that we will in time just come to know. 1 standard deviation, about 2/3 of the data. 2 standard deviations, about 95% of the data. 3 standard deviations, virtually all the data. Let's see how they work out in practice. The people who put the SAT together deliberately designed the test so the scores on it are scaled to follow a normal distribution. An average score on an SAT math, say, is 500, and the standard deviation is 100 points. What that means is, since mean is 500, standard deviation is 100, and 1 standard deviation out is 2/3 of the data, start at 500, go down 1 chunk of 100, you're at 400, go up 1 chunk of 100, you're at 600. We'll have about 2/3 of the SAT scores between 400 and 600. The SAT is designed to concentrate scores toward the middle, and most people will score in this 400 to 600 range. Go out 2 standard deviations and you'll have 95% of the data. Start at 500, go down 2 chunks of 100, you're at 300. Go up 2 chunks of 100, and almost everybody, 95% of the population, 19 people out of 20, will have scores between 300 and 700. Of the remaining 5%, half of them will be down below the 300, i.e. 2.5% of the population, and the other top 2.5% of the population will be up here above 700. If you score 700 or better, you're doing very well, top 2%. Virtually all the data lie within 3 standard deviations, that is 200 to 800. Why do scores on the SAT run 200 to 800? Because of the normal curve. It's designed so that pretty much everybody falls between 200 and 800. It is actually technically possible to score below a 200 or above an 800, and they just round it off to 200, 800. Everybody's between 3 standard deviations. And so, key points. For normal data, typical data, common data, usual data, ordinary circumstances, for a normal situation, about 2/3 of the data will be within 1 standard deviation of the mean. About 95% of the data will be within 2 standard deviations of the mean, and virtually all of the data will be within 3 standard deviations of the mean. These 3 benchmarks are numbers we will use again and again and again, and by repetition you will find that you will just be committing them to memory. We should know these benchmarks.